Welcome to the deep dive. So, you're here because you want to get a solid handle on operating systems, right? Especially thinking about that fourth course in the Google Cybersecurity Certificate, Tools of the Trade, Linux, and SQL.
Yeah, exactly.
You want the key stuff, the essentials for a cybersecurity analyst, but without getting, totally overwhelmed.
Right. Think of this as the quick path to understanding this really foundational topic.
Okay.
We've looked through, quite a bit of material. Basic overviews, comparisons of different OSs, how they actually talk to hardware and software, virtualization, which is super important, and the whole GUI versus command line thing.
So clicking versus typing.
Pretty much.
Plus.
And our mission really is just to give you that solid base, what an OS does, the common ones, how you interact, and why it all matters so much for cybersecurity.
Perfect. Let's dive straight in then. What's the absolute core function? It always feels like this invisible engine making things run.
That's a good way to put it. It's basically the critical link, the go-between connecting the computer's physical parts, the hardware, with you, the user, and the software you're running.
The translator and coordinator.
Exactly. It takes your requests via the software and tells the hardware what needs to happen, making sure it all works together.
Okay, I like analogies. It's kind of like ordering in a restaurant.
How so?
Well, you tell the waiter, maybe that's the app what you want. The waiter takes the order to the kitchen, the OS.
Okay, I follow.
And the kitchen uses the stove, ingredients, the hardware to make the food, which comes back to you.
That actually works really well.
Yeah.
So, a bit more formally, any task involves this sort of four-part flow. Starts with you, the user.
Right.
You make a request to an application. The app talks to the operating system. The OS then tells the hardware what to do.
And then it comes back.
Then it reverses. Hardware reports back to the OS. OS updates the application, and the application shows the result. Back to you.
Okay, walk me through a simple example, like downloading a file. I do that all the time.
Sure. So you click the download link in your browser. That's the application.
Yeah.
The browser tells the operating system, hey, user wants this file. The OS then directs the hardware, specifically your network card.
Right, the thing that connects to the internet.
Exactly. It tells it to fetch the data. As the data comes in, the network card tells the OS.
Okay.
The OS then tells the browser application, here's the progress, and the browser shows you that little download bar filling up.
Got it. User, app, OS, hardware, then back up the chain. Simple enough. But hang on, before any of that, the computer has to start up. What happens right at the beginning?
The boot process.
Yeah.
Good point. When you hit that power button, it's actually a tiny chip with firmware that kicks things off.
Firmware, like BIOS. I remember that from older machines.
Exactly. BIOS. Basic input-output system on older ones.
Yeah.
Newer systems mostly use UEFI, Unified Extensible Firmware Interface.
More modern.
Yeah, more features, more flexible, but both basically do the same initial job. Run a quick check, make sure the essential hardware is okay.
Power on self-test. POST.
That's the one. And then the very last thing BIOS, or UEFI, does is hand off control to something called the bootloader.
Bootloader, okay.
And the bootloader's only job is to find the main operating system on your storage drive and load it into the computer's memory, the RAM. Once the OS is loaded, then you can start interacting.
Okay, that makes sense. So OS is loaded. We know what it does. Now, what about the different types? Windows, Mac, Linux are the big ones I hear about.
You're definitely major players, especially in the desktop world. You've got Windows, been around since, 1985? It's closed source.
Meaning the code isn't public?
Right. Microsoft keeps that proprietary.
Yeah.
Then macOS, which actually started back in 84. It's interesting. It's partially open source.
Partially. How does that work?
The core part, the kernel, they call it XNU, is open source. But a lot of the user interface and the built-in apps, that's all closed.
Okay. And then there's Linux. That always seems central to security discussions.
It really is. Linux popped up around 1991, and the key thing is it's completely open source.
And why is that so vital for security?
Well, because anyone can look at the code. Security researchers, hobbyists, developers all over the world, they can inspect it, find potential weaknesses, suggest fixes.
So more eyes on the code means potentially finding and fixing problems faster.
That's the idea, compared to closed source,
Yeah.
where only the vendor's internal team can see it. This community collaboration is a huge reason Linux is so dominant in servers, infrastructure, and especially the security field. We'll even see specific Linux versions, distributions, built just for security work later in the course.
Right. What about others? Chrome OS, Android.iOS.
A good question. Chrome OS, relatively newer, 2011. It's also partially open source, built on the fully open source Chromium OS project, often found in schools on Chromebooks.
Okay.
Androids for mobile devices. That started around 2008. It's open source, based on the Linux kernel, actually.
Ah, interesting connection.
And then iOS, Apple's mobile OS since 2007. Like macOS, it's partially open source.
Yeah.
4 parts are open, but the user-facing stuff isn't.
So, recapping the source code thing. Linux and Android are fully open. Windows is closed. Mac and iOS are kind of hybrids.
You got it. And that open nature of Linux and Android is definitely a factor in their widespread use and scrutiny in the tech world.
Okay, clear on the main players. Now, how do we actually use them? You mentioned clicking icons versus typing commands earlier. Is that the main difference in how we interact?
That's pretty much the core distinction, yeah. We call them the graphical user interface, GUI, and the command line interface, CLI.
GUI is what most people use day to day, right?
Yeah.
Icons, windows, mouse pointers.
Exactly. Very visual, very point and click or touch based. The CLI is, well, it's text. You type commands, the computer types back responses.
We've got an image here showing just that a familiar desktop next to that, black screen with text. Looks very different. But does it work differently?
Fundamentally, yes.
Yeah.
With the GUI, you're usually doing one thing at a time. Click this icon, open that menu, drag this file.
Right. One action, one result.
Mostly. With a CLI, though, you can string commands together. You can tell it to do multiple things sequentially, or even pipe the output of one command directly into another. It's potentially way more powerful and efficient.
If you know the commands, I guess.
That's the key. There's a learning curve. But once you know them, you can automate complex tasks, manage systems much faster. Think about creating, say, 100 user accounts. Clicking through a GUI. That'd take ages.
Yeah.
On a CLI, you could potentially do it with 1 or 2 lines of scripted commands.
Okay, so efficiency is a big plus for the CLI, especially for repetitive or complex tasks common in security. You mentioned another advantage, though. Something about history.
Ah, yes. The command history. This is huge, especially in Linux and similar systems. The CLI automatically keeps a log file of basically every command you type.
A log file. Why is that useful?
Couple of reasons. For incident response, say you're following a documented procedure, a playbook, to contain a breach. You can literally go back through your command history to verify you executed every single step correctly.
Ah, like an audit trail for your own actions.
Exactly. Helps avoid mistakes, ensures consistency. But even more critically, if a system has been compromised, that command history can be gold for forensic analysis.
How so?
You might be able to see the attacker's commands, assuming they use the CLI. What files did they access? What tools did they run? When did they do it? It's like finding their footprints.
Wow, okay. That's a powerful feature I hadn't really considered. So CLI isn't just about speed, it's also about traceability.
Definitely. Huge advantage in security investigations.
All right, so we interact with the OS, it does its job. But nothing's perfect. Let's talk about security flaws, vulnerabilities. Is this just something unavoidable?
Unfortunately, yes. In any complex piece of software, like an OS, there are going to be bugs, and some of those bugs will have security implications. It's a constant cat-and-mouse game. Researchers find flaws, vendors patch them, attackers try to exploit them before or after the patch.
And one area that seems particularly risky is legacy systems, right? What exactly are those?
Legacy operating systems are basically older versions that are no longer supported or updated by the vendor. Think Windows XP or maybe older server versions.
But why would anyone still use them if they're outdated and unsupported?
Often it comes down to compatibility. Maybe they have critical business software that was written decades ago and only runs on that specific old OS.
Oh, wow.
Or think about industrial control systems like in manufacturing plants or utilities. Those systems might have embedded software tied to an old OS, and upgrading is incredibly complex, expensive, and potentially disruptive.
So they're stuck, in a way, but the risk?
The risk is huge. Because they don't get security updates, any vulnerability discovered after support ended remains unpatched. Forever. Attackers know this, and they actively scan for these legacy systems because they're often easy targets.
Yikes. Okay, so avoiding legacy systems is ideal. But even with modern, updated systems, vulnerabilities still exist.
Absolutely. New flaws are found all the time, even in the latest versions of Windows, macOS, Linux, iOS, Android, everything. That's why staying informed is critical for security pros.
Where do people look for that info?
There are official channels. Microsoft has the Microsoft Security Response Center, MSRC. They publish details on vulnerabilities, usually with the CVE number.
CVE.
Common vulnerabilities and exposures. It's like a standard ID number for a specific flaw. Makes it easy to track and reference. You can see recent ones they listed in, say, April 2025 for Azure Functions or the Edge browser.
Okay, and Apple.Linux.
Apple has its Apple Security Updates page. They just released patches, like April 16th, 2025 for iOS 18.4.1 and macOS Sequoia 15.4.1, listing the CVEs they fixed. For Linux, it depends a bit on the distribution, but resources like the CVE report for Ubuntu are common. Even cloud providers like Google Cloud have bulletins they noted issues in Looker and the Linux kernel affecting their services around late April 2025.
So keeping systems patched is job one, but knowing where to look for newly discovered vulnerability information is just as important.
Crucial. You need to be aware of the current threats, even for fully patched systems, and definitely understand the risks if you encounter legacy environments.
Makes sense. You need the full picture. Okay, we've mostly talked about OSs running directly on the physical machine, but there's virtualization too, right? Running an OS inside another OS.
That's the basic idea, yeah. Virtualization uses software to create virtual or simulated versions of computer hardware.
Like a fake computer running inside my real one.
Pretty much. We call that a virtual machine, or VM. It's software that emulates a CPU, RAM, storage, network card, all the bits of a physical computer. This lets you run a complete separate operating system instance within a window on your host machine.
And you can run multiple VMs at once.
Yep. On a single physical computer, you can host several VMs, each potentially running a different OS, all sharing the underlying physical resources like memory and CPU power. We have that image showing one physical box running 3 different VMs.
Why is this so useful for cybersecurity folks?
2 main reasons: security and efficiency. For security, VMs provide isolation. You can set up a VM as a sandbox.
A safe place to play?
Sort of. A safe place to analyze suspicious files or malware. If the malware detonates inside the VM, it's supposed to be contained there, not affecting your main operating system or other VMs.
Supposed to be?
Well, strong isolation, but maybe not 100% foolproof. There have been rare cases of VM escape vulnerabilities, but generally it's a very effective way to handle risky stuff safely.
Okay, so isolation for safety. What about efficiency?
Big gains there. As a security analyst, you want to test something on Windows, Linux, and macOS, or use specific tools that only run on one OS instead of needing 3 physical machines.
You just spin up 3 VMs on your one powerful laptop or desktop.
Exactly. You can run different environments side by side, switch between them easily. It streamlines testing, analysis, development, way more efficient than juggling physical hardware, like using one bus instead of 50 cars.
Got it. And what's the software that manages all these VMs called?
That's the hypervisor. The hypervisor is the layer of software, sometimes it's even built into the OS kernel, that creates, runs, and manages the virtual machines. It handles allocating physical resources like CPU time and RAM to the different VMs.
Any specific hypervisors to know?
One key one, especially if you're getting into Linux, is KVM kernel-based virtual machine. It's open source and actually built into the Linux kernel itself. Makes Linux a very powerful virtualization host right out of the box.
Okay, and VMs aren't the only kind of virtualization.
Right. You can virtualize other things too, like servers, storage, even entire networks. It's all about abstracting the underlying physical stuff using software. But VMs are probably the most common type you'll interact with directly.
Wow, okay. We have definitely covered a lot of ground, really quickly but thoroughly, I think. Let's try and wrap this up with the main takeaways.
Sounds good. So first, remember, the OS is that crucial intermediary user, apps, hardware. It manages the conversation.
Right, the translator.
And knowing the common players, Windows, macOS, and especially Linux, because of its open source nature and security focus, is key.
And the ways we interact. GUI for visual ease, CLI for power, efficiency, and that super useful command history for analysis.
Don't forget vulnerabilities. They're everywhere, even in updated systems. Legacy OS are extra risky because they don't get patched.
To stay informed using things like MSRC, Apple Security Updates, CVE reports, keep patching.
Absolutely. And finally, virtualization. Using VMs is a standard practice now for security pros.
Giving you that safe, isolated sandbox environment and the efficiency to run multiple OSs and tools on one machine.
Exactly. Isolation and efficiency are the big wins there.
Okay. So, as you, our listener, continue with the Google Cybersecurity Certificate, especially digging into Linux and SQL in this course, really hold on to these OS fundamentals. They underpin so much else.
They really do. And maybe a final thought to leave you with. As software gets more complex, systems get more interconnected, think about how the operating system itself might need to change. How might its role evolve to handle future security threats? And what new skills might you, as a future security analyst, need to master in that changing landscape.
That's definitely something to chew on. How does this foundation prepare you for what's next? Good stuff to consider.